All right. Hi, everyone. My name's Katherine Shepard, and today I'm going to be going over the second lab that you're going to do this semester, which is on Kepler's laws of planetary motion. So, for right now, I just have the lab pulled up. This is what you should see when you have your PDF or Word document downloaded. You've got your overview, your objectives, the definitions. These are really helpful if, while you're going through a question, you don't understand a term. You can always come back and check the definitions. And then it goes into getting the lab set up. Now, this is the most complicated part of the lab, so follow my steps with me or take notes, whatever you need to do. So what you're going to do is you're going to go to whatever web browser you like to use, and you're going to Google VLab GSU. And then you should have technology.gsu.edu, VLab, Virtual Lab, GSU Technologies should be the first link that pops up. Go ahead and click that. And that will take you to GSU's Virtual Lab page. Yep, it should look just like this. And then you have a red Login to VLab button on the right. Go ahead and click that. You should have a separate tab pop up. From here, you need to select the right option. You want to use the HTML access. You want to use the HTML access instead of downloading anything and installing it. So go ahead and click HTML access. And from there, it should ask you to accept their terms of service, and then you'll log in. Right, so here are your terms of service. Whoops, sorry about that. I'm having an issue with my keychain. So go ahead and just accept their terms of service, and then go ahead and sign in with your usual GSU, PAWS, and iCollege login information. Now, when you're logging in, make sure you select GSU AD from the drop-down menu at the bottom. Do not select DMD or it won't work. Go ahead and select GSU AD. So then I'll just go ahead and log in. Perfect. So once you're at this page, you need to go ahead up here to the upper right-hand corner, and you want to select this gears symbol, like this gear symbol, or settings, whatever you normally have for settings. Now, if you have a newer computer, like I have a 2018 MacBook Air, so mine's a little older, and so I do not have a high-resolution option. But if you do have a high-resolution option on this page, you need to enable it. Otherwise, the simulation won't work. So make sure you check this to see if you have the high-res option. If you do, allow it or enable it. Go ahead and save whatever changes you make and then close out of it. So then once you've done that, you want to click the only thing on the screen, which is the VLab student image file, and it has a little computer on it. Go ahead and click that. Notice it gives you a little notification saying all data is deleted when you sign out. So if you're in the middle of the simulation, it might be better to just complete it all in one go rather than sign out. But you're not going to be getting any data that you need to save in this. So this isn't really a problem for us right now. So just go ahead and click OK. And what this is doing is it's logging you in to the lab computers that we would have and be using if we were in person. So you're seeing the desktop. And so even though I'm on a Mac, I'm seeing a Windows desktop. So from here, go ahead to the bottom left-hand corner and click the Windows icon. From here, click Astro UNL. And then from that drop-down menu, click NAAP Labs. And this will start opening up our simulation. Don't worry about Teams if you have a Teams thing pop up. We're not working in Teams, so go ahead and just exit out of that. So from this screen, from your NAAP Labs screen, go ahead and click number 5, Planetary Orbits, from the left-hand listed menu. Then from your Planetary Orbits page, click Kepler's Laws of Planetary Motion. And it'll take you through a whole bunch of background information on like what the laws are on. If you want to scroll on this, you have to use the scroll bar on the side. Otherwise, your computer will freak out and think you're doing something else. So if you need a refresher on what the first, second, and third laws are, and what they talk about, then this would be a good thing to read before you start the lab. But it's background information, so if you think you know them pretty well, you can just go on ahead and click Next Page. And then this is giving a different perspective on the 3 laws from Newton's laws of like mechanics point of view. So don't need to worry about this too much. Go ahead and click Next Page. And then click the big image that's like a preview of what the simulator is going to look like. Go ahead and click that, and it should launch your simulator. So this is what your simulator should look like. You should have an image of what your orbit looks like in the upper left-hand corner. Then you have, below that, you have 4 tabs. You have Kepler's first law, Kepler's second law, and Kepler's third law. And then Newtonian features. We're not going to worry about Newtonian features. Make sure you have Kepler's first law, that tab, selected. From here, from the little box that corresponds to Kepler's first law, make sure we're following the directions on the lab now, so you can follow along with me. Part 1, Kepler's first law. In this introductory paragraph, it tells you what you need to click to set up the simulator. So, first you're going to click Show Empty Focus. You should have a nice little X pop up in your simulator window. And then you're going to click Show Center and Show Semi-Major Axis. Make sure you have semi-major axis and not semi-minor axis. They're 2 different axes. The semi-major axis is half of the longest axis in the ellipse, whereas the semi-minor axis is half of the shortest axis in your ellipse. So, no semi-minor, only the semi-major. So, from here, we just want to point out on the right-hand side of your simulator window, you have 3 panels. You have orbit settings. This is what you're going to be using most often. You're going to be adjusting your semi-major axis, your eccentricity, and you're going to be selecting different planets to view the information for. Then you have animation controls, such as start animation and the animation rate. How fast do you want it to go? And then you have visualization options. You could show the solar system orbits, and you could show a grid. We're not going to use these at all. You don't need to worry about them. So, to start off, the lab asks you question 1 and 2 is asking basically what happens to the shape of the ellipse when eccentricity gets larger and then when eccentricity gets smaller. So for this, you're just going to go to your simulation window. You're going to take the eccentricity bar. You're going to slide it way down. So for question 1, what happens to the shape of your orbit, which is this outside line that the planet draws as it orbits around? What happens to that as you lower the eccentricity, as it gets closer to 0? And what happens to it as you raise it, as it gets closer to 1? Now, eccentricity is a measure, I like to say, of how eccentric the orbit is, right? So we've all got like an eccentric family member. Like if you have an eccentric aunt, they're a little wonky, they're a little all over the place. You're kind of like, yeah, they're just a little eccentric. Don't mind them. You can think of an orbit as the same way. More eccentric is more elongated, it's more of an oval, and a lower eccentricity is more of a circle, where an eccentricity of 0 equals a perfect circle, and eccentricity of 1 is actually unbound. So anything less than 1 will be really elongated, assuming it's close to 1. It'll be really elongated, it'll be an oval. Once you reach 1, your orbit becomes a parabola, where it's like a comet. You have the comet coming in towards whatever object is at one of your foci. Its path gets altered by the gravity of that object, and it flies off the screen again, never to be seen. And these are not comets like Halley's Comet that comes around, every couple hundred years or so. These are comets that come in once and we never see them again, hence unbound. So, I've just given you the answer to number 1 and number 2. Also, pay attention to how I'm just going to call this the sun, how your object inside the circle that your planet is orbiting around, how that shifts with respect to the foci, the empty foci and the foci that it was at. Pay attention to how that shifts, and you can use that in your questions as well, like, oh, it gets closer to the center of the circle, or it gets further away and moves towards one of the foci. So that's how you answer number 1 and 2. Then, number 3, change the value of the eccentricity until the orbit becomes circular in shape. What is the eccentricity of a circular orbit? I just said that, so I gave that away to you. If you need to find out, just go ahead and lower the eccentricity as far as it'll go, and that'll be as close to a perfect circle as you can get. So, now we're going to look at planets. We're not just going to look at some random body orbiting the sun. We're going to look at actual planets of our solar system. So we're going to fill out this table. Table 1, planet eccentricities and semi-major axes. So the first one is Mercury. So you will go up here to your orbit settings. You'll click the drop-down menu. You'll select Mercury, and then you'll click OK. And you can see the shape of the orbit and the position of the sun has changed from where I put it because I messed around with the eccentricity. So from here, you're just going to write down the number that is given in both of these boxes. And pay attention to this. People accidentally flip this stuff all the time, that the first number is the semi-major axis, and this goes in the second column, or the third column, the second empty column. And the eccentricity is the bottom one, and that goes in your first empty column. So just pay attention to the labels and put them in the correct spots. So then, from here, once you've filled all this out, make sure you fill it all out. It's super easy, and it's worth, a decent chunk of the lab because it's a table. So number 4, which planet has the most circular orbit? Hint, remember that a perfect circle has an eccentricity equal to 0. Now this just gave away the answer to one of those previous questions again, if you were confused on that. So make sure you got the question that asks, what's the eccentricity of a perfect circle? Make sure you got that one right. So which planet has the most circular orbit? You want to come up here to your table. You want to look at all the values you've written down for your eccentricity, and you want to find the lowest one. Now remember that some of these may be like 0.096, 0.3, or 0.007. So when you're comparing this, these are not the correct numbers, by the way. When you're comparing these, you want to pay attention to how many zeros it is away from the decimal. So what I have for Venus is 0.3. That would actually be the largest one, even though the number 3 is the smallest between 9 and 7, because of the place it's in relative to the decimal point, it's actually the largest. You would say this is 3/10 of 1, or something like that. For 0.096, you would say that this is 96/100ths of 1. So this would be smaller than 0.3 because 1/100th is smaller than 1/10. And then if you looked at the value I have written down for Earth, 0.007, this would be your smallest number because you have 2 zeros between the decimal and the first number that you have, the first number greater than 0. And this would be equal to 7/1000ths of 1, right? So you've got 3/10, 96/100ths, and 7/1000ths. So this is a much, much smaller number than either of these. So this would be your smallest, and this would be your largest. So, question 4 just asks you to look through your table, find the smallest eccentricity. Again, make sure you're looking at the eccentricity and not the semi-major axis. And then question 5 asks you to do the opposite. It asks you to find the highest value for eccentricity. So for me, that would be Venus, 0.3. Again, these are not the correct numbers. You need to get the correct numbers from your simulator. Now, question 6, in my opinion, is the most tricky question. It's the question that's most easy to overthink. So, what it asks is that during Kepler's lifetime in the early 17th century, only Mercury, Venus, Earth, Mars, Jupiter, and Saturn were known planets. Tycho Brahe told Kepler that the data for the position of Mars were the most difficult to match using a circular orbit. Based on this information, Kepler selected the orbit of Mars as the starting point to developing his first law of planetary motion. So, number 6 asks, briefly discuss why the orbit of Mars was so difficult to reconcile with a circular orbit. Hint, look at the eccentricity of Mars's orbit. Now, I'll tell you right now, Mars has the highest eccentricity. Second highest eccentricity that you'll get from your simulator. So it is very, very elliptical. It's very elongated. And actually, as a matter of fact, the simulator is wrong in this respect because Mars is actually the most eccentric orbit. In real life, it has the most eccentric orbit out of any of the planets. So, knowing that Mars has the most eccentric orbit out of any of the planets, that scientists at this point had not discovered Uranus and Neptune, didn't know they existed. Why do you think Mars's orbit was so difficult to reconcile with a circular orbit? And the key is to look at the first law of planetary motion. Now, the first law of planetary motion basically just says that the orbit of each planet is an ellipse with the sun at one focus. So think about how people would try to predict or how they would try to test whether an orbit was an ellipse or a circle. For me, what comes to mind is trying to predict where a planet would be at a certain time. Because if a planet is this far away from the sun, and it has a circular orbit, then we should be able to predict where it's going to be in a certain amount of time. However, if one of the things you're basing that prediction on is wrong, such as the assumption that it's a circular orbit, it won't be in the right position that you predicted it to be. It'll be somewhere else. So think about that. Think about why you think the orbit of Mars was so difficult to make it match their theories. And don't be afraid to ask us about this. Like I said, I think this is the most difficult question of the entire lab, so just do your best and then come to one of our discussion sections for help. So, before proceeding to the next part, make sure you click Reset near the top right corner of the app to refresh the simulation display. So I'm back over to the simulator. If I go up to the upper right-hand corner, it has Reset, Help, and About. Click Reset. Okay. Now we're moving on to Kepler's second law. So from here, you want to go to the Kepler's second law tab. We've been on Kepler's first law this whole time. Now we're going to Kepler's second law. So for this one, you want to click Start Animation. And yours will be nice and smooth. And what you want to pay attention to is how fast this planet is moving over here at perihelion, which is the point closest to the body that it's orbiting around, in this case the sun, and how fast it moves when it's way over here, which is at aphelion, which is the point furthest from the body it's orbiting, or the sun. So, question 7 asks you, describe how the orbital speed of the planet changes when it is near aphelion first, so the furthest point away from the sun. So you want to get as far away from this body as you can. It's going to be over here. How does the speed of your planet change here versus when it's over here at its perihelion? And then question 8 asks you to do the opposite. Describe how the speed changes when it is near perihelion, the closest point to the sun. So then how does the speed change when it's here versus when it's over here? So just pay attention with that one to where you're looking at and what you're comparing the speed to. And all we're looking for is it speeds up or it slows down. That's all we're looking for. So they're going to click Stop Animation. I've already stopped mine because my computer is so laggy. And what you want to do is you want to go down here to the box where you control Kepler's second law and all of the parameters and stuff we're going to be working with. And you want to drag this Adjust Size bar until the text beneath it, which says a fractional sweep size of 1/16 or 6.3%. You want to drag that over to the right until it says a fractional sweep size of 1/7 or 14.3%. Okay, there we go. Very nice. See, 1/7 or 14.3%. Then you want to click Sweep Continuously. So once you have this set up, you want to click Start Sweeping. And you want to watch as the planet orbits around, it'll sweep out all of these different areas. Now, Kepler's second law is a little difficult to understand. It basically says that the area contained within each of these triangles is the same, no matter where you are in the circle, because each of these was swept out over the same amount of time. So, say I gave it 1 second to sweep out an area. They would sweep out this much at this point and this much at this point. Now, to help this make sense, the area of a triangle, which we can equate these two, is equal to 1/2 the base of your triangle, which is the portion that is outlined by the orbit, versus the height, which would be how far the edge of the orbit is from your sun. So you can see that this triangle here near perihelion has a much larger base but a much shorter height versus one that's over here near aphelion, which has a much smaller base but a larger height. And so those two will kind of equal themselves out, and so the area contained within those two triangles is the exact same, even though they're in different places. So then number 9 says, if you split the orbit into 7 equal time periods, meaning each sweep has the same area, but are the shapes of each area the same? If no, describe how they're different. So this is worded a little funky. Basically what it says is we have split this orbit up into 7 parts. That's why we set it to 1/7 fractional sweep size. And if you can even count it, you can go 1, 2, 3, 4, 5, 6, 7. We have 7 triangles. And what it's asking is, each of these is the same area, but are they the same shapes? Yes, they're all triangles, sure, but do they all have the same height? Do they all have the same base? How are those shapes different? So that's what we're looking for in number 9. And then number 10, your answer to number 9 should have been no. The areas are the same, but the shapes vary. So that just gave you the answer to number 9. We're looking for a bit more than that. I would like you to describe how the shapes vary. But yeah, that gives you the answer to number 9. And then it says, in order to keep in line with equal time equals equal area, how does the speed of the planet change in different areas? And that's again just getting at why is the base of this triangle that's over here near aphelion, why is that a smaller base than the base of the triangle that's here near perihelion? And this is trying to have you look back at number 7 and number 8. How fast is the planet moving in both of those spots? So then, moving on, we're going to go ahead and click Reset again, because we're moving on to the third law. So then, from here, you want to select Kepler's third law, and this gives you the equation. This is the only law that has an equation, and what it basically says is that the amount of time it takes a planet to orbit the sun is related to the planet's average distance from the sun. So basically, Mercury, which is really, really close to the sun, will orbit the sun really fast, versus, say, Uranus, which is way out there. And you'll see just how far out there it is later on in the semester. And a planet that is so far out there is going to take quite a long time to orbit the sun just once, because it's covering a significantly larger amount of distance. So, in this equation, you have p raised to the power of 2, we call that p squared, and that is equal to a raised to the power of 3, or a cubed, where p is the orbital period of your planet in years. You have to make sure your units are right. And a is the semi-major axis, or the average distance from the sun, in AU. And AU is an astronomical unit, and it's given in your definitions. It is the mean distance between the sun and the earth, because we're based on Earth, and so we like to say, space is really, really large. It's impractical to measure things in miles and kilometers and stuff like that. We need bigger measurement units. So we're going to say the distance from the Earth to the sun is just about 1 AU, and that is equal to 1.5 times 10 to the 8 kilometers. And that 1.5 times 10 to the 8 kilometers, let me make this larger so you can see what I'm writing. 1.5 times 10 to the 8 kilometers is 1, 2, 3, 4, 5, 6, 7 zeros after it. AKA, I have moved the decimal point to the right because it is raised to a positive value 8 spaces. So I move it to the right once to get 15 with a period on the side, and then it's followed by 7 zeros because I have 7 times left that I need to move the decimal. So 1 AU is equal to 150 million kilometers. So that's quite a long way. So going back down to the third law, it's going to ask you to calculate some stuff. So using this equation and the semi-major axis values that you got in table 1, remember table 1 is where we found the eccentricity in the semi-major axis. So using the semi-major axis, you want to calculate the orbital period of each planet. So I will do the first one with you, and I'm going to give you the formula. So the original formula is p squared equals a cubed. And we can rewrite this to be more useful. We're calculating the orbital period, so we want to isolate p. So we can rewrite this as p equals the square root of a cubed. So whenever I'm doing this formula, I like to go to a site that's called Wolfram Alpha. Wolf like the creature that howls. And then am, and then alpha. So it's kind of like saying, like, I'm a wolf and I am the alpha. But wolframalpha.com, and if it'll ever load, it's a great calculating website that I love dearly. I'm going to wait for it to load and then I'll be back. All right, I am back. So this is what Wolfram Alpha should look like. If it gives you a whole bunch of options about what kind of math you want to do, just pick whatever, like basic algebra, and that'll be just fine. So the way that you would type this in is squirt with parentheses, and then you would do inside those parentheses another set of parentheses, caret 3. And then you would write your semi-major axis inside this very inner portion of parentheses. So, for the first one I need the semi-major axis of Mercury. So going back to the table, what you should have gotten for the semi-major axis of Mercury is 0.387. So I'm going to write 0.387 inside these parentheses, and then hit enter. And it should do the calculation for you. You just have to make sure you have your parentheses set up correctly, otherwise it will do it wrong. All right, and here we are. Here are our results. It tells us this is what you put in, so you can make sure that you've typed it in correctly. And then it gives you your answer under results. So the answer for table 2 from Mercury is 0.24, and then you can leave it at that, or you can go 0.2407. You do not have to write out all of these decimals. You can just round it if you know how to round. Otherwise, just write the first 2 or 3 numbers after the decimal, and that'll be just fine. So you're going to fill out this whole table just by using this formula that I've given you. And then you're going to move on to the final part of the lab, which is applying this to a real life scenario, which is looking at 2 different comets. The first one is Halley's Comet. We all know Halley's Comet. And the other one is a name that I cannot pronounce, otherwise known as 67P. Excuse me. So the important things that you need to find in these paragraphs are the eccentricities and the semi-major axes. So for the first paragraph for Halley's Comet, it says it has an orbital eccentricity of 0.967 and a semi-major axis of 17.94 AU. You need to keep those numbers in mind, or underline them or highlight them or whatever. And then you need to look at 67P, and you see down at the bottom it has an orbital eccentricity of 0.632 and a semi-major axis of 3.51. So Question 11 asks you to compare the eccentricities of the comet and state which one has a higher eccentricity. So again, you just want to look at the eccentricity, which is 0.967 versus 0.632. Which of those is a larger number? And then you want to say, Halley's Comet has a higher eccentricity. And then it asks you to describe what the orbital shape of the comet with the higher eccentricity would look like. Meaning, given that eccentricity, is the orbit going to look like a circle? Is it going to look like an ellipse? Is it going to look like a parabola? AKA, is it perfectly circular? Is it an ellipse? Or is it unbound? Then, number 12, using equation 1 and the semi-major axis values given above, calculate the orbital periods of the two comets. So you do the same thing you just did for table 2, using this equation, p equals the square root of the cubed root of a. Sorry, no. P equals the square root of a cubed. Sorry about that. So you just want to use that equation. You can use Wolfram alpha again. You should still have that equation set up, nice and easy. And you can just take the orbital periods given for Halley's Comet and 67P, plug those into the formula, and then write down what the answers are. And again, just to point out, you need the semi-major axes values, and so the semi-major axis of Halley's Comet is 17.94, and the semi-major axis of 67P is 3.51. So you just want to plug those in and calculate it. And then the very last question, and this is kind of cool, I think. It says, Halley's Comet was last at perihelion in 1986, meaning it was last at the point closest to the sun in 1986. At that point, it was people on Earth were able to view it with their naked eye, aka as a naked eye comet. When at perihelion, it can be seen without the use of a telescope or any other instrument. And that is awesome. Like, how often are you able to see a comet without any help? No binoculars, no telescope, no nothing. So then using your answer from question 12, which is where you calculated the two orbital periods, what year do we expect the next opportunity to see Halley's Comet with our unaided eye to be? And this is a nice and simple addition problem. So you want to take 1986, which was the last year we saw it, and you want to add the orbital period, which let's say the orbital period is 100 years. That means that we would next be able to see Halley's Comet in 2086. And that's all it's asking for. That's not the correct answer. You'll have to do the math yourself. But yeah, that is how you do that. And with that, that is the end of this lab. And just a fun activity to do is think about how old you'll be the next time we'll be able to see Halley's Comet. I will personally be almost 80 years old. I will be ancient. So that'll be really cool for me to be able to see that before I die. And so, yeah, I will leave it at that. Make sure to come to our discussion sections if you have any questions, and we'd be happy to answer them or clarify anything that you may be confused on. So with that, I will see you guys later. Stay safe.